Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. In this lesson, we will learn about oracles. We will first get an introductory understanding of what oracles do. Then we will delve into the concept of decentralized oracle networks. Before delving into oracles, let us take a minute to understand the determinism property of blockchain smart contracts. Determinism of smart contract refers to the property that when a transaction triggers the execution of a smart contract, the result would be identical across each node the smart contract is executed. Consider a smart contract similar to one used in Compound, which calculates the value of your crypto collateral based on the price of tokens quoted in a centralized exchange like Coinbase. The input is the price of tokens on Coinbase and the output is the value of collateral. We will call it the valuation smart contract. The company that sponsors this decentralized finance app is called LoanWise. Every 5 minutes, an automated transaction is initiated from a LoanWise-owned EOA and directed towards the valuation smart contract. On receiving the transaction, the valuation smart contract pulls data from a centralized exchange like Coinbase by using the latter's API. Once the transaction triggers contract execution, the code is executed by each node on the blockchain individually. The problem is that there could be tiny lags of 1 or 2 seconds when the transaction reaches the different nodes. Hence, input values procured via the Coinbase API may not be identical for each node. If the input value is not the same, the output will not be identical and hence the property of determinism is violated. Smart contracts are prevented from procuring information from external data sources for the sake of determinism. However, this creates a problem as smart contracts require off-chain data elements ranging from token prices to weather data, depending on the use case. Hence, an Oracle smart contract enters into the picture. The Oracle is a type of smart contract, which simply pulls data from external sources via APIs. We can identify 2 entities involved in this Oracle illustration. 1 is the owner of the decentralized finance app. In our example, this is a fintech called LoanWise Corporation. 2nd is the Oracle entity. In this example, let us call this company Truthful Corporation. Next, we will redo the illustration with an Oracle in the picture. A LoanWise EOA initiates a transaction to the valuation smart contract. The valuation smart contract determines that it needs external data and hence it initiates a transaction to an Oracle smart contract, which is owned by Truthful. Ether is transferred from the requesting smart contract to the Oracle smart contract. This is because LoanWise must pay a small fee for every data request to Truthful. This fee is separate from the gas fees paid to the blockchain. We can call the valuation smart contract a requesting smart contract, since it is requesting data from the Oracle smart contract. One of the Ethereum nodes is connected to an off-chain node owned by the Oracle. On receiving the query from the requesting smart contract, the blockchain node sends a request to an off-chain node to procure data via an API call, in this case to a centralized exchange like Coinbase. The off-chain node receives the data and sends the data to the Oracle smart contract via a transaction. As the transaction gets confirmed into blocks, all the nodes on the blockchain now have this data. We can now go back to the valuation smart contract. As we noted, when the transaction was triggered to run the valuation contract, it initiated a process which updated the Oracle smart contract. While executing the valuation contract, each node pulls a specified value from the Oracle smart contract on the blockchain. All outputs are identical and hence, the condition of determinism is met. An oracle is a service provider who procures data from off-chain sources for input into smart contracts in the blockchain. The accuracy of oracle source data is critical because once a smart contract is executed, the transaction cannot be reversed. For instance, in the Compound app example that we studied in the previous lesson, once collateral is seized and liquidated, the action cannot be reversed. Hence, it is critical that the price data fed to a smart contract is accurate. The example that we just reviewed is a centralized service provider model where smart contracts rely on one party to procure and publish accurate off-chain data, thus creating a single point of failure. In our example, if Truthful procured or published incorrect data, there is no backup plan. An alternative to a centralized model is a decentralized oracle network that relies on multiple providers to procure accurate data from multiple sources. In the next section, we will learn about decentralized oracle networks. We will use the abbreviation DON to refer to such networks, the most famous of which is Chainlink. While Chainlink is the most well-known, there are many decentralized oracle platforms, each of which it operates somewhat differently. Hence, in this section, we will cover a basic overview with the understanding that each platform operates somewhat differently. A decentralized Oracle network consists of two components, on-chain and off-chain. The on-chain component consists of smart contracts. The second component is the decentralized Oracle network that resides off-chain. Data is actually procured off-chain. We will first learn how the off-chain component procures data using an illustration. In this illustration, the data requested is the 52-week low stock price of Amazon. Assume there are 3 Oracle nodes that specialize in procuring financial information. Note that these nodes or computers are not part of the blockchain network, but they can communicate with the blockchain. In our example, Node 1 procures information from Yahoo Finance and Bloomberg. Node 2 procures information from Bloomberg and Reuters. Node 3 procures information from a startup called TickerTalk. The nodes pay for API access to these data sources and will be compensated via the fee collected from the end-user smart contracts who are requesting this data. The following data points are collected by each node. However, there is a problem. The data sourced by the third node does not match with the other data sources. What has actually happened is that TickerTalk is publishing incorrect data. Amazon did a 20-for-1 stock split and TickerTalk is inaccurately not adjusting historical data for the stock split. This brings us to an important question. How should data points procured from multiple sources, some of which may be erroneous, be aggregated? Next, we will discuss aggregation. A decentralized Oracle network deploys aggregation algorithms that can aggregate the responses of multiple Oracle node operators. For instance, in our illustration, the algorithm can exclude outliers and calculate the average of the remaining. The nature of the aggregation algorithm will vary depending on whether the information sought is numeric or qualitative. There are 2 options. In option 1, all nodes send their data to an on-chain smart contract via transactions and a smart contract executes the aggregation algorithm on-chain. In option 2, aggregation is done off-chain and data is placed on the blockchain only once via a single transaction. Option 1 is an expensive option since gas is expended for 3 transactions. In addition, gas is expended on executing the aggregation smart contract. In option 2, only 1 transaction is sent to the blockchain. Option 2 is more scalable for permissionless blockchains like Ethereum. With permission blockchains, the gas fees are lower and hence option 1 is feasible. Node operators are individuals or businesses that run nodes of the decentralized Oracle network. They procure data, perform computations and convert the data into blockchain-readable format. They transmit the data payload to an on-chain smart contract via transactions. The nodes are independent and do not communicate with each other. Oracle node operators get paid a fees from the data purchasers. For example, Chainlink node operators get paid in Link tokens, which is an ERC20 token issued by Chainlink. The gas fees a node operator pays is denominated in Ether. This exposes the node operator to foreign exchange risk. For example, say an Oracle node operator on the Chainlink network quotes a fixed fees of 10 Link tokens for answering one query. But Ether becomes more expensive over time while the dollar price of Link tokens in centralized exchanges remain the same. Hence, the gas it is paying in Ether gets costlier while the fees received in Link tokens remains the same. Hence, the node operator must keep the price it quotes to end users updated on a dynamic basis. We can see that a decentralized Oracle network seeks to promote accuracy via 2 levels of decentralization. Decentralization of oracles means that there are multiple nodes procuring data independently. Decentralization of sources means that each node is sourcing data from multiple sources. The sources may overlap between different nodes. This kind of configuration is referred to as a decentralized Oracle network. Now that we understand how data is procured, we can map the entire workflow. There are 5 steps. Request. Oracle selection. Data procurement. Aggregation. Callback. Next, we will review each one in turn. The process begins with a transaction reaching the smart contract of the data purchaser. Let us say in this case, it is a DeFi app. The smart contract realizes that external data is required. Hence it sends a transaction to an Oracle-owned smart contract. The Oracle smart contract must decide which Oracle to route the transaction to. We will review that part of the process next. The purchaser of the data must specify the following in their request. First, the query parameters of the information they are seeking. Second, the desired number of Oracle nodes to source the information. Finally, the promised payment in the specified token. In Chainlink, the payment is in the form of Link tokens, an ERC20 token issued by Chainlink. When a new request is registered by the on-chain smart contract, an off-chain log visible to Oracle node operators is updated. Oracles can bid to fulfill the order with their fee quote. Qualified bids must meet certain criteria, which could differ across Oracle platforms. An example of a criteria is that the bit received must be from node operators who are eligible to provide data of a particular type. For instance, the node operators eligible for supplying weather data may be different than for financial markets data. Another example of a criteria is that the Oracle node operator meets a specified reputation score of the purchaser as based on a reputation management system established by the Oracle platform. Once the desired number of qualified bids are received, the selected Oracle nodes are given the green signal to procure data from respective data sources. The nodes pull data from off-chain sources via APIs. They may also perform certain computations on the raw data received. They convert the data to a blockchain-readable form. Aggregation, as we discussed previously, is the process of taking data from multiple oracles and converting it to one correct answer based on defined rules. The Oracle node that has the aggregated data sends the data via a transaction to the Ethereum node it is connected to. Remember that the Oracle nodes are themselves not part of the blockchain and hence, communicate information only with the blockchain nodes they are directly connected to. Once the Oracle smart contract is updated with the requested data, it sends the data via transaction to purchasers requesting smart contract. On receipt of this data, the purchaser's smart contract can execute its design function, which could range from valuation of collateral to determining the winner of a bet on an election result. We can now see how a decentralized Oracle network divides the workflow into on-chain and off-chain components to minimize gas fees. Only the first and the last step occur on-chain. However, not all blockchains are as gas-intensive as Ethereum. We earlier learnt about Polygon, which is a Level 2 platform with much lower gas fees. Further, permission blockchains have few nodes and since the participants are trusted entities, do not need the proof-of-stake type consensus mechanisms. Hence, their transaction processing fees is low. This means that for certain blockchains, the entire workflow can occur on-chain. That is obviously not the case with Ethereum. The workflow of a decentralized Oracle network seems quite straightforward. However, behind this apparent simplicity, there are complex technical challenges which a decentralized network must address. These include confidentiality, node misbehavior and collusion attacks. Next, we will learn what these are. Understanding how these challenges are addressed is beyond our scope. For this course, we will restrict ourselves to knowing what they are. It is helpful to note that solving for these challenges with human intervention is not very difficult. But a decentralized Oracle network, in consonance with blockchain ethos, aims to solve these problems programmatically. Confidentiality references the technical ability to hide the data being requested on a public blockchain through encryption. The reason this is important is that for many use cases, confidentiality of data is critical. For instance, a hedge fund may not want the world to know that it is requesting data on certain securities as it gives away their trading strategy. Node operators can misbehave in many ways. Freeloading refers to an Oracle node operator who is simply replicating the responses of other node operators instead of incurring the charges necessary for procuring the data independently from the prescribed sources. Another example is non-performance. Nodes could make bids and when awarded the bid, simply pocket the fees and not execute the data request. Collusion is a very specific type of node operator misbehavior. A group of node operators can collude to submit incorrect data for financial gain. For instance, if the smart contract is an options contract where one of the parties gains financially if the price of securities is above or below a certain level, misreporting the securities data can be beneficial to the colluders. To summarize, a decentralized Oracle network facilitates accurate transfer of off-chain data to on-chain by relying on decentralization and algorithms, instead of reliance on manual curation by a central party. This brings us to the end of this lesson on oracles. Please review the summary of this lesson and proceed to the final wrap-up lesson of this course.